Imagine standing on the edge of infinity, gazing into the heart of our world, a realm so profound, so hidden, that it defies our wildest imagination. Deep beneath your feet, more than 5,000 kilometers down, pulses the Earth's inner core, a searing sphere of iron and nickel, hotter than the surface of the sun, yet solid as steel under unimaginable pressure. It's the dynamo that powers our planet's magnetic shield, protecting us from cosmic radiation. But what forged this colossal engine? What unseen forces sculpted it from chaos? Today, we're diving into a radical idea: Earth's core, built by cosmic dust. The unseen truth might just rewrite the story of our origins. Let's start at the beginning, when the universe was young and wild. About 4.6 billion years ago, our solar system was born from a swirling cloud of gas and dust, the solar nebula, left over from the death throes of ancient stars. This wasn't just any dust, it was cosmic dust, microscopic grains forged in the fiery hearts of supernova, enriched with heavy elements like iron, nickel, and even traces of carbon. These tiny travelers, no bigger than grains of sand, hurtled through space at speeds up to 70 kilometers per second, carrying the building blocks of worlds. Picture it, a vast disk orbiting a newborn sun, cooling and condensing. Gravity, that relentless architect, began pulling these particles together. At first it was gentle, static cling on a cosmic scale. Dust grains collided and stuck, forming fluffy aggregates called chondrules, the oldest solids in the solar system. Over millions of years these grew into pebbles, then boulders, and finally planetesimals, kilometer-sized rocks tumbling through the void. This is the accretion process, the cornerstone of planetary formation. But here's the twist. Without that initial cosmic dust, nothing happens. It's the seed from which giants grow. Earth wasn't built in a day. It took a frantic 30 million years of bombardment. Early on, our protoplanet was a molten hellscape, a magma ocean hundreds of kilometers deep, fed by endless impacts from asteroids and comets, remnants of that same cosmic dust. These collisions delivered not just mass but heat, vaporizing rock and metal alike. Iron meteorites we find today? They're fossils from those chaotic times, chunks of shattered asteroid cores that mirror what was sinking into Earth's depths. Now, the real magic: differentiation. As the magma ocean churned, denser materials gravitated toward the center. Iron and nickel, heavier than silicates, began their inexorable plunge. But how? For decades, scientists pictured a global melt, where the entire young Earth liquefied, allowing metals to pool like oil and water. Yet recent models challenge that. NASA's percolating core theory suggests something subtler: molten iron droplets percolating through a partially solid mantle, like hot wax through a sponge. No need for total meltdown, just targeted heat from impacts and radioactive decay. And what fueled those droplets? You guessed it. Cosmic dust, laced with hydrophile elements, iron-loving metals, that hitched a ride from the nebula. Evidence? Look to the rocks. Iron isotope ratios in Earth's mantle match those in enstatite chondrites, rare meteorites thought to hail from our planet's birth materials. A 2020 study from the University of Chicago analyzed these signatures, revealing that Earth accreted rapidly, perhaps in just a minute and a half of cosmic time, from vaporized dust. That's not hyperbole. Simulations show the final stages of growth happening in a flash, as a Mars-sized protoplanet slammed into us, birthing the moon and kickstarting core formation. But the core isn't just iron. Seismic waves rippling through Earth during earthquakes paint a portrait of its anatomy. The outer core, a 200-kilometer-thick liquid layer, swirls with convective currents, generating our magnetic field via the geodynamo effect. Deeper still, the inner core solidifies slowly, growing about a millimeter a year as heat escapes. It's mostly iron, alloyed with nickel and lighter elements like sulfur or oxygen, up to 10% by weight. These impurities keep it from freezing solid, lowering the melting point in a process called supercooling. Enter the unseen truth: carbon. In September 2025, researchers at the University of Leeds dropped a bombshell. Their experiments, squeezing diamond anvil cells to mimic core pressures, showed that just 2.4% carbon by mass could explain the inner core's existence. Without it, the core would have frozen too early, dooming our magnetic field. Where did this carbon come from? Cosmic dust, of course. Supernovae spew carbon-rich grains and carbonaceous chondrites, primitive meteorites, deliver it in spades. Over billions of years, trillions of tons of this dust rained down, not just building the core, but seeding the chemistry for life itself. Imagine, The same stardust that crystallized our planet's heart might have sparked the first amino acids in primordial soups. Yet, the core isn't static. February 2025 brought seismic shocks, literally. Teams from USC and Cornell, poring over earthquake data from the past 2 decades, detected the inner core's outer boundary warping like a melting ice cube. It's less solid than we thought, with patches of mushy iron crystals deforming under tidal stresses from the moon and sun. This shapeshifting could tweak Earth's rotation, subtly shortening or lengthening our 24-hour day by milliseconds. More alarmingly, it hints at deeper instability. Satellite swarms like Swarm have spotted magnetic anomalies near the core mantle boundary, plumes of hot material rising, perhaps stirred by ancient impacts or convective upheavals. Why does this matter? Our core isn't just a relic, it's alive, evolving. The magnetic field it generates deflects solar wind, shielding our atmosphere from stripping away like Mars. Without it, life as we know it vanishes. And cosmic dust? It's not ancient history. Every year, 40,000 tons of micrometeorites pepper Earth, injecting fresh metals into the atmosphere. Some ablate on entry, fertilizing oceans with iron, a key nutrient for plankton, the base of our food chain. But let's zoom out. If Earth's core owes its birth to cosmic dust, what does that say about exoplanets? Telescopes like JWST are spotting worlds around distant stars, some with iron cores inferred from density. The percolation model could explain super-Earths with oversized hearts, formed in dustier disks. And on icy moons like Europa, buried oceans might churn with metallic snow from similar processes, hinting at subsurface life forged from the stars. Of course, mysteries linger. Is the inner core truly spherical, or does it wobble like a cosmic top? How much hydrogen lurks in those liquid layers influencing dynamo chaos? And could giant impacts, like the one that made the moon, have delivered the final dust payload that tipped the scales? Experiments at synchrotrons and supercomputers push boundaries, but the core's depths remain veiled. As we peel back these layers, one truth emerges: we are stardust, through and through. The iron in your blood, forged in a supernova, accreted into cosmic dust, sunk into Earth's core, and cycled back via volcanoes and erosion. That beating heart below isn't alien, it's us. A 4.5 billion-year symphony of gravity, heat, and humble grains. So next time you feel the ground tremble or watch the aurora dance, remember, beneath it all lies the unseen truth. Earth's core, built by cosmic dust, a testament to the universe's quiet alchemy. What wonders still hide in those depths? The stars know, and perhaps one day, so will we.